Okay, so for today, we've got probably two sections that we can get through. The first one being 3.3, linear systems of ODEs. So, let's just return to what we were talking about before. Every first order linear homogeneous, let's try this again. Every first order linear system of ODEs looks like this. We have x1 prime equaling some function of t times x1 plus some function of t times x2 plus dot 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 plus some function of t times xn, and then possibly some other function of t. That would be the inhomogeneous term. And x2 prime equals a 2, 1 of t x2, or not x2, x1, plus a 2, 2 of t x2 plus dot 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 plus a 2n of t xn plus b2 of t dot 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 xn prime equals a n1 of t x1 plus a n2 of t x2 plus dot 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 plus a n of t xn plus bn of t. Every linear I keep being in the habit of saying linear homogeneous. Every linear system of ODEs looks like this, okay? And n is as many variables as you please. For us, it's usually going to be 2. But in any case, this can be rephrased as a matrix equation. You can rewrite this as x1 prime, x2 prime, dot dot dot, xn prime, all together in a vector equals a11 of t, a12 of t, dot dot dot, a1n of t, a21 of t, a22 of t, dot dot dot, a2n of t, dot dot dot, dot dot dot, dot dot dot, dot dot dot, a n1 of t, a n2 of t, dot dot dot, a n of t, multiplied by the vector x1, x2, dot dot dot, xn, and then add to this b1 of t, b2 of t, dot dot dot, bn of t. Okay? So in this way we can rewrite a huge system of ODEs, a huge first order linear system of ODEs, as one single ODE, okay? And we often refer to this vector right here as z vector prime. We often refer to this matrix as A of t. This vector is z vector, and this vector is b vector of t. So in other words, what I'm saying is every linear system of ODEs can be rewritten as a single vector ODE that looks like z prime equals a of t z plus b of t. And it's a homogeneous system if b of t is the zero vector. Wait, this is a vector. And it's a it's a homogeneous system if b vector of t is the zero vector. Okay? So we're mainly going to focus in this class on first order linear homogeneous systems of ODEs with constant coefficients. That means that this b vector is the zero vector, and this matrix here does not depend on t, so it's just a matrix of constants. So for that we have a theorem. This is the solution theorem for linear homogeneous systems of ODEs. So let z vector prime equal a of t times z vector be a linear homogeneous system where a of t is an n by n matrix of functions of t. So here n is some integer, of course, some positive integer. If z1 vector and z2 vector and dot 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 all the way up to zn vector are linearly independent, solutions of the ODE, which just means that when you take the derivative of this, you get the matrix times this. Then the general solution is z vector of t equals c1 z vector z1 vector plus c2 z2 vector plus dot 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 plus cn zn vector. For some constants c1, c2, all the way up through cn, you know, the usual thing. Okay, so what I'm saying here is in order to work with the theory of linear homogeneous systems of ODEs, we're back to this situation where we need to find a bunch of linearly independent basis solutions and then just take the linear combinations of those, and that will be the general solution. Okay? Right, so that's all there is in 3.3. So let's move on to 3.4. Is the eigenvalue method. Now, they really shouldn't call 3.4 the eigenvalue method, because both 3.4 and 3.7 are about the eigenvalue method. And those will be what we spend the remainder of the class on. So might not get through everything today, but that's fine. We have time in the course. So first of all, we need to define what an eigenvalue actually is. So definition. Let A be an n by n matrix. So it's a square matrix, same number of rows as columns. An eigenvalue of A is a complex number lambda such that there exists a non-zero vector V satisfying the equation A times V vector equals lambda times V vector. Okay, so by the way, I'm saying lambda is a complex number. That doesn't mean that it has to have an imaginary part. So in other words, it could be a real number too. Real numbers are complex numbers after all. They just have imaginary parts that are zero. So an eigenvalue is a number such that there exists a vector out there that's not the zero vector, and the matrix times that vector is the same as the scalar lambda times that vector. Okay. In that case, V vector is called an eigenvector of A associated to lambda. Okay. So the simplest example of an eigenvalue would be if I take what's called the 2 by 2 identity. So first of all, I should define this for you. The n by n identity matrix looks like ones along the diagonal and zeros elsewhere. So the 2 by 2 identity matrix is 1, 0, 0, 1. Okay? And it's denoted by I2 for 2 by 2 identity matrix. Now, let's just notice that if you take 1, 0, 0, 1, and you multiply it by the vector 1, 0, what you get back is, well, let's see here. 1 times 1 is 1, plus 0 times 0 is 0. So we have 1 in the first row, first column. Then 0 times 1 is 0, plus 1 times 0 is 0, so we have 0 in the second row, first column. In fact, this happens for not just 1, 0, but actually every vector out there. So if I made this AB, 2 by 2 identity matrix has the property that when you multiply it by any two-dimensional vector, you just get back that two-dimensional vector. Okay? Now I want to notice that this is 1 times that two-dimensional vector. Right? So what we say here is that 1 is an eigenvalue of the 2 by 2 identity matrix. And any vector you like is an associated eigenvector. Well, okay. By definition, the eigenvector has to be non-zero. So any non-zero vector is an associated eigenvector. Okay? So that's sort of the simplest example you could possibly think of. Let's talk about how to actually compute these eigenvalues, because not every eigenvalue is going to be as easy to find as this. Okay? So if you've got an n by n matrix with an eigenvalue lambda and an associated eigenvector v, then you are satisfying this equation. That's the definition of eigenvalue and eigenvector. Okay? I want to point out this is the exact same thing as a times v vector minus lambda times v vector equals the 0 vector. Right? Next, I want to point out that if you replace lambda v by lambda times the n by n identity matrix times v, then you haven't changed anything, because the identity matrix times v is always v. And then I want to notice that you can factor out v vector. So you can write this as a minus lambda in times v vector equals the 0 vector. And once again, can't emphasize enough, v, the eigenvector, has to be not the 0 vector. Okay? So what we're looking for is a non-zero vector that satisfies this vector equation, this matrix equation, I should say. Well, we have a theorem for that. We have a theorem that says that there is a non-trivial solution to this equation if and only if the determinant of this matrix right here is 0. And I made a mistake in the last lecture because I said it has to be non-zero. So in the description of that previous video, I clarified it should be 0. But in any case, yes, the determinant here, this is true if and only if the determinant of a minus lambda in is 0. This right here is an expression called the characteristic equation of the matrix. And the left-hand side is called the characteristic polynomial. Once you find the roots of the characteristic polynomial, you have the eigenvalues. Okay? So, of course, we're going to do some examples. I suppose I don't really want to erase this. Yeah, I don't want to erase this. I know, we can just do the example using the blank space. Okay, example. Actually, now that I think about it, sorry, I'm a mess today. Now that I think about it, we should probably do it on this side because this is where all the talk about eigenvalues actually is. So let's do it over here. Example. Okay, I'm gonna say the matrix A is 2, 1, 1, 2. I want to find the eigenvalues and associated eigenvectors. For this matrix. Okay, well, in order to make that happen, what we need to do is have A times V vector be lambda times V vector, with V vector not being the zero vector, sorry. Okay. Again, that's the same as saying that the determinant of A minus lambda I2 is 0. So what we need to do here is take the determinant of A minus lambda I2. So, we're looking at the determinant of the matrix A is 2, 1, 1, 2, and subtract from this lambda times the 2 by 2 identity matrix 1, 0, 0, 1, and this is supposed to be 0. This is the same as the determinant of 2 minus lambda, 1, 1, 2 minus lambda equals 0. Okay, so now we need to take the determinant of this 2 by 2 matrix. You multiply it through, you get 2 minus lambda squared minus 1 times 1 equals 0. Then this turns into 4 minus 4 lambda plus lambda squared minus 1 equals 0. And so lambda squared minus 4 lambda plus 3 equals 0. This is what we call the characteristic equation of the matrix. As long as we can find the solutions of the characteristic equation, we'll have the eigenvalues. We're not done yet, by the way. I'm just pausing here because I'm about to erase the left-hand side. So if you want to keep looking at it, I suggest pausing the video. So this right here can be factored. This can turn into lambda minus 3 times lambda minus 1 equals 0. That gives us two roots, two distinct real roots. One of them is 3. And the other one is 1. And those would be the eigenvalues of our matrix. Okay? Now, there was one other thing that I asked for, and that's for the eigenvectors. So in order to find the eigenvectors, what you have to use is just this same equation again, but now realize that lambda is either 3 or 1. So let's start with lambda equals 3. this looks like a v vector equals 3 v vector, where v vector is not the 0 vector. This is the same as saying 2, 1, 1, 2 times some vector is going to be 3 times that same vector, and again, that vector better not be the 0 vector. So if it's a vector, then it's going to have 2 entries. So let's call those entries A and B for no particular reason. So let's replace this v vector by the vector A, B on both sides. Okay? And if we can solve for A and B, then we'll be done. So you look at this and you realize, well, this is the same as saying 2A plus B equals 3A. And meanwhile, A plus 2B equals 3B. Okay. Now, if you subtract 2A from the first equation, you get B equals A. At the same time, if you subtract 2B from the second equation, you get A equals B. Well, that seems kind of redundant. The truth is, you will always have a redundant system of equations when you do this. So all we have to do to find an eigenvector associated to 3 is take any non-zero value whatsoever and consider that to be A. Okay, so for no other reason than we need something, I'm just going to say, by choice, A is going to be 1. All right, in that case, v vector, let's call this v1 because we're also going to have a v2. That would be AB. That would be 1, and then according to this equation right here, B is equal to A, so B is also 1. So this right here is an eigenvector associated to this eigenvalue. Okay? And the truth is, as I said, we chose A to be 1. It didn't have to be 1. It could have been any non-zero number whatsoever. But let's just make it 1. Okay? All right, let's look at the other eigenvalue, which is 1. So once again, we're searching for vectors v2 such that A times v2 is 1 times v2, and v2 had better not be the 0 vector. So this is the same as saying 2, 1, 1, 2 times, let's call it CD now, equals 1 times CD. You multiply through, you get 2C plus D equals C, and 1C plus 2D equals D. Subtract 2C from the first equation, and what you get here is D equals negative C. So again, the second equation says the same thing. So we're going to make a choice. We're going to choose C to be 1, in which case V2 vector, which is CD, becomes 1, and then D is negative 1. And then that is an eigenvector associated to the eigenvalue 1. Okay? And this is always how it works. First thing you've got to do is find the eigenvalues, which you do by setting the determinant of A minus lambda times the identity matrix equal to 0. That gives you the characteristic equation. You solve the characteristic equation to find the eigenvalues. And then for each eigenvalue, you find the eigenvectors associated to it. You do that by just plugging it back into this equation right here, understanding that lambda is whatever value you found. Okay? So of course we're going to do some more examples. So, example. Find the eigenvalues and associated eigenvectors of the matrix A being equal to 1, 1, negative 1, 1. All right, so what we've got to do is we've got to say the determinant of A minus lambda I2 needs to be 0. So this is the determinant of 1, 1, negative 1, 1 minus lambda 0, 0, lambda. This needs to be 0. So this is the determinant of 1 minus lambda, 1, negative 1, 1 minus lambda. This needs to be 0. All right, so you take this determinant. What you get here is 1 minus lambda squared minus negative 1 times 1. This needs to be 0. This turns into 1 minus 2 lambda, 1 minus 2 lambda plus lambda squared plus 1 equals 0. Therefore, we're looking at lambda squared minus 2 lambda plus 2 equals 0. Now, you might notice that this is not factorable. In fact, the discriminant is negative, so we're going to have non-real eigenvalues this time. And that is fine. So, negative b plus or minus the square root of b squared minus 4ac divided by 2a, just using the quadratic formula, right? This turns into 2 plus or minus the square root of 4 minus 8 is negative 4. Then divide this by 2. This turns into 2 plus or minus 2i divided by 2, which is 1 plus or minus I. Okay. So the eigenvalues, we have two different eigenvalues. One of them is 1 plus I, the other one is 1 minus I. Now, when you're finding the associated eigenvectors, just like, well, when you're finding the associated eigenvectors, you only need one of those in the complex conjugate pair. So we're just going to take 1 plus I for now. So lambda equals 1 plus I. We need to have A times V vector equals 1 plus I times V vector, with V vector not being the 0 vector. This is 1, 1, negative 1, 1, multiplied by AB equals 1 plus I times AB. Multiply through and you get A plus B equals 1 plus I times A. And then negative A plus B equals 1 plus I times B. Okay, so if you subtract A from the first equation, what you get here is B equals I times A. Okay? So now we're going to make the choice. A equals 1. In that case, this vector here, V vector, is AB. And that's just going to be 1 I, which is I times 1. And that right there is an eigenvector associated to the eigenvalue 1 plus I. Okay? And like I said, we only need to select the plus in 1 plus or minus I, because it's a complex conjugate pair and they're going to give the same information. Okay. So here we have a non-real eigenvalue and a non-real entry eigenvector. That is fine. That can certainly happen. And let's try another one. Let's say we have 3, 1, 0, 3. And we're trying to once again find the eigenvalues and associated eigenvectors. So we need the determinant of A minus lambda I2 is equal to 0. So that would be 3 minus lambda, 1, 0, 3 minus lambda. This needs to be 0. You do the determinant, you get 3 minus lambda squared minus 0 equals 0. This turns into lambda squared minus 6 lambda. Well, actually, no. Why am I distributing it when it's already factored for us? It's already factored for us as 3 minus lambda squared equals 0. So therefore lambda has to be 3. Okay. Now, let's notice that this is also a weird situation, because now we have a repeated eigenvalue. We have a multiplicity greater than 1. That will turn out to be a real hassle eventually, but not today. So let's find the eigenvectors associated to lambda equals 3. So what we have to do is take A times V vector equals 3 V vector, with V vector not being the 0 vector. So this looks like 3, 1, 0, 3 times a vector like AB equals 3 times AB. You multiply through, you get 3A plus B equals 3A. And meanwhile, 0A plus 3B equals 3B. You subtract 3A from both sides of the first equation, and what you get here is B equals 0. That's the only condition. So we can make the choice A equals 1. If you do that, then V vector becomes AB, which is going to be 1, and then apparently B is 0. And that would be the eigenvector associated to the eigenvalue 3. Okay? So you might be wondering, why do we care about eigenvalues and associated eigenvectors? There is a good reason. Let's suppose you have a matrix A, and it has an eigenvalue lambda with an associated eigenvector called V vector. Okay. I want to look at Z vector of t equals V vector times e to the lambda t, a vector valued function. Well, let's just take the derivative of that. Z vector prime of t is equal to V vector times lambda times e to the lambda t. Now V vector times lambda is A times V, because that's the definition of an eigenvalue and eigenvector. But then this thing right here is Z. So this just becomes A Z vector of t, which means that Z vector of t is actually a solution of this ODE. Z vector prime equals A of t Z vector. Okay? And so what we're going to end up doing is we're going to end up finding the eigenvalues and associated eigenvectors, constructing solutions that look like this, then If those are linearly independent, we'll be able to apply the solution theorem to find the general solution. Okay? But that'll be for a future lecture because we are out of time for today. So see you in the next one.